Okay, this is the 1.2 video continued, so part 2 of 1.2. So in the first video I asked you to do these example 3 problems and also to find the domain and range. So it did say use your graphing calculator on this one, so you should have gotten this upper half of a circle. Mine doesn't look that great. So if you look at the graph, you can see your x values are all here between -2 and 2. And you can have the value x equals -2. If I plug -2 in here, I get -2 squared, which is 4. 4 minus 4 is 0. Square root of 0 is 0. So I have this point, -2, 0. That's a point on my graph. So my domain includes -2 and 2. So that's why I use the brackets. So this is my domain. Any x value between -2 and 2 and including -2 and 2. And my range, so these are my y values. So you want to think y values. So you can see I don't have any y values down here. I don't have any negative y values. So my first y value is right here where y is 0. So y equals 0 is the lowest y value on this graph, and the highest y value on this graph, ooh, this is a mistake, should have a bracket there, is 2. So y values go from 0 to 2. 0 and 2 are both included, so that's my range. This graph I like to call, it reminds me of how you drew seagulls when you were in 2nd grade. The seagull graph, kind of a fun one. So if you think about domain and range, this graph goes forever in this direction and it keeps going up. So all of these x values forever and ever and ever are on my graph, and all of these negative x values are on my graph. So my domain is all real numbers. This is the symbol for all real numbers. I call it that double leg R. This is also how you can identify domain. It goes from -infinity to +infinity. And remember, whenever we're using infinity here to describe domain and range, we always use the parenthesis, not the bracket, because it can't include infinity or -infinity, because infinity and -infinity are not a number. And then if you look at your y values, well, you can see y equals -1, -2, -3. I have no negative y's on my graph. So my lowest y value is 0, and then I go up forever. Even this y value, y equals 9, would eventually be a point on this graph. So the smallest y value is 0, and I can have at y equal to 0. And then y goes up forever to +infinity, open parenthesis. Or you could also identify it like this. It would be more like this: y such that y is greater than or equal to 0. Okay, so that's hopefully what you found for domain and range. Okay, now we need to talk about even and odd functions. These come up a lot in calculus, and we're going to do note study cards as we go through the class. This would be the first note study card I will have you write. So if you want to do index cards, whatever you want to do, this is going to be the first definition you put on those study cards. Even and odd functions, and I would put exactly what you see here. So this says when you plug in a negative value for x, you get the same output that you would get if you plugged in a positive value for x. This says if you plug in a negative value for x, you get the negative of the function. So I like to picture in my head for an even function, I like to picture a quadratic, symmetrical about the y-axis. So this is the graph. When I try to think even or odd, I picture a quadratic. So when I put in, so if I have y equals x squared, when I put in +2, I get 4, and when I put in -2, I get 4. So my output is the same if I put in the positive or the negative input. 4 an odd function, I like to picture y equals x, that diagonal line. So this one, if I put in, say, x equals 1, I get y equals 1. But if I put in x equals negative 1, I get y equals negative 1. So f of negative 1 equals negative f of x. So that's odd. Y equals x to the third would also be odd. So that picture looks like this. So these are symmetrical about the origin. So this point flips about the origin. This point flips about the origin. So let's try a couple. Well, I already told you x squared is even. But let's justify our answer. So let's do, I'm going to write this f of 1. So if x is 1, I'm going to get 2 times 1 squared. That's going to equal 2. If I do f of negative 1, I'm going to get 2 times negative 1 squared. Negative times a negative is a positive, so I'm going to get 2 again. So if I put in 1 and if I put in negative 1, my output is the same. Also, this exponent is even. That's an even function. Mostly. But here, when you have a quantity squared, we want to check it. So I'm going to do f of 1. I just like 1 because it's easy to work with. I'm going to get 1 plus 1 squared. That's 2 squared. That equals 4. And now I'm going to do f of negative 1. That's x plus negative 1. Oops. How about negative 1 plus 1 squared? That's 0. So we're not even. And we're also not odd because negative f of x would be negative x plus 1 squared. And that's not going to be 0. So I'm not even, I'm not odd, so this one I'm neither. Okay, if I put in, because when I put in negative 1, I get 0. I would not get the negative of that. Plain old x equals 5, that's going to be odd. But let's prove it. F of 1 equals 1 to the 5th, which equals 1. F of negative 1 equals negative 1 to the 5th. That's going to be negative 1. So this is negative f of x. So this is an odd function. That's what an odd will look like. X to the third minus 1. So I'm going to do f of 1 is going to equal 1 to the third is 1. 1 minus 1 is 0. F of negative 1 is going to be negative 1 to the third minus 1. This is going to be negative 1. Negative 1 minus 1 is going to be negative 2. So I'm not even. Now I want to check if I were odd. So I'm going to see what negative f of x looks like. That's going to be this. X to the third minus 1. So if I distribute this negative, that's going to be negative x to the third minus 1. So if I plug in a negative 1 in here, I'm going to have negative 1 to the third, negative out front, and a 1. I'm going to work this way now. And that's going to be negative 1. Negative times a negative is a positive. So that's going to be positive 1. Oops, should this be... Oh, this should be a plus. Sorry. Distribute that negative. That should be a plus. So negative 1 to the third is negative 1. Negative 1 times negative 1 is positive 1. Positive 1 plus 1 is 2. So f of negative 1 does not equal negative f of x. So this is also a neither. Cosine. Well, if you picture the cosine graph, let me slide up here. Cosine of 0 is 1, so it looks like this, right? It looks symmetrical about the y-axis. It is even. Let's show why. So I'm going to do f of pi over 2. F of pi over 2 is cosine of pi over 2. So cosine of pi over 2 is 0. And I'm going to do f of negative pi over 2. Cosine of negative pi over 2 is also 0. So that's even. Now sine, remember sine goes through 0, 0. Sine is not even, sine is actually odd. So let's show why. So f of pi over 2 for sine, sine of pi over 2 is 1. F of negative pi over 2 is negative 1. So this is odd. So that's why you need to remember the definition so you can do this test, because this is what would be required if you were asked to justify that you're even or odd. Okay, a lot in this section. This is already an 11-minute video. I'm going to go on. It's going to be another longer one. All right, so this is piecewise functions. I am going to tell you that you can type these into Desmos just as you're learning them. But this one we can pretty easily graph by hand. So these are my functions. Negative x, so think that's just the line y equals negative x. The second function is x squared. Well, that's just x squared. And the third function is 1. So these are all lines. Oh, no, that's a parabola. These are lines, but this isn't too bad. Now I just have to limit them to these x values. So the first one, y equals negative x. Well, remember y equals negative x is this diagonal line that goes through the origin, but negative. Now I'm going to do this light because I think I'm going to have to erase part of it. This is when x is less than 0. So that's all of these x values. So this function, I'm going to erase this bottom part, because from 0 and anything less than 0, this is how my function is defined. And then I look at the next restriction. Between 0 and 1, I'm x squared. So between here and here, I'm x squared. Well, we know what this function does. It does this, right? This is y equals x squared. So between here, I'm just going to kind of draw in a little curve there. I'm x squared, including 1, so I have a closed dot there. And here I include 0 too, so I have a closed circle here. And then when x is greater than 1, so all x values here, I'm this line, y equals 1. So that looks like this. So that's the graph of that piecewise function. You just got to take it in pieces. All right, so this is a line. This is a horizontal line. And this is the parabola again. So this says when x is less than negative 2. So I'm going to go to negative 2 here, and I think I need to graph this line 2x plus 3. So what I do sometimes is I graph the whole line. So this has a y-intercept of 3 and a slope of 2, so up 2 over 1. I'm going to go down 2 and to the left, down 2 and to the left, down 2 and to the left. So that's the line. But this is just going to be from negative 2 to the left. So x is negative 2. Here's the point on the line when x is negative 2. So this is going to do this. And I don't need that part. And I also, it doesn't include negative 2, so I really should put an open circle there for now. Okay, now from negative 2 to 2, and including both of those endpoints, I'm the line y equals 4. So y equals 4. 1, 2, 3, 4 is up here, so this is the line y equals 4. Draw it light first because we're going to erase some. And this is going to be from negative 2 So I'm going to stop it right here at -2, and I'm going to put a closed circle because it includes -2. X is greater than or equal to -2 all the way to +2. So I'm going to do another closed circle there, and I'm going to erase here. This is also why you should never do calculus with a pen. Okay, so there's the second piece. First piece, second piece. -2 is not included here, so that's an open circle. -2 is included here, so that's a closed circle. And now for greater than -2, so anything over here, I am x squared. So let's think about that graph, x and x squared. So 0, 0, 1, 1, 2, 4, 3, 9. So over 2, up 1, 2, 3, 4. Oh, that's that point right there. Over 3, up 1, 2, 3, 4, 5, 6, 7, 8, 9. That's that point. So from here over and greater than 2, I'm going to try to make this look parabola-ish, a parabola. So that's not the best parabola, but it'll have to do. Okay? This 2 we already colored in here, so that would be a closed circle. Okay. Absolute value. So picture in your head, what does that absolute value graph looks like? Looks like this, right? Has this point at 0, 0. So when I look at this, the first thing I think is this -1 means it is, so the parent function is just y equals absolute value of x, which looks like that. So this -1 means it's going to be shifted down 1, and this -2 means it's going to be shifted 2 to the right. So you can think about this point is going to go down 1 and to the right 2. So down 1 to the right 2. So that's where the bottom of my V is going to be. And then it's just going to continue up looking like the absolute value graph. And if you did a table of values, you would get these points. But if you know that the translations down and to the right, negative goes to the right, remember, then you don't really need to do all of the table of values. Now let's do domain and range for this. The domain for absolute value is always going to be all real numbers, because any x value can be on that graph. So that's the interval from -infinity to +infinity. And the range, think of your y values. This is the lowest y value, right? This point over 2 down -1. That y value is my lowest y value. And then it goes up forever. So this is y must be greater than or equal to -1. Or -1 to infinity is the interval where all my y values exist. Okay, one more quick review of composition. I love composition. So fun. This says f of g of x, so it looks like g of x is inside of f of x, and that's what we're going to do. Remember, this is also written, not like that. This is also written like this, with that little open circle. I like to call this fog, because students find compositions foggy sometimes. So either one of these ways of writing it you might see. So this means put g of x inside of f of x. So I always find the inside, I always work from the inside out. I think the inside function is going into the outside function. So I'm replacing this x with this. So f of g of x is going to equal, f is on the outside, but in place of x, I'm going to put x squared. So x squared minus 7. This is f of x squared minus 7, with g of x put inside of it. Now this is just saying, well, what if you have x equals 2 and x equals 2? So this is composing the functions and putting a number inside. So we already have f of g of x. So f of g of 2 is just going to be 2 squared minus 7. So that's going to be 4 minus 7. That's going to be negative 3. Now, g of f of 2, that's this one. Couple ways of doing it. First way is do the composition backwards. So now I want to put f inside of g. So this is what I would have, f x minus 7 squared. Okay, x, that's the same as this, x minus 7 times x minus 7. That's the same as x squared minus 14x plus 49. And then I would put 2 in there. 2 squared minus 14 times 2 plus 49. And I think I get 25, I believe. Check my math on that one. The other thing that I think is a lot easier is first you find f of 2. So f of 2 would be plug 2 in there. I would get 2 minus 7. And that would be negative 5. And then put negative 5 in g. So then I would do g of negative 5 would be negative 5 squared, 25. So that way's, right? You can see that way's a lot shorter. All right, that's it for 1, 2, right? Or 1, 3. What are we doing here? We're doing 1, 2, the continuation of 1, 2. Okay, so now you have all the 1, 2 notes.